Okay, so what's the date? The 20th. Oh my God, time flies. So you guys submitted your exam last week. I'm almost done with. So I think I mentioned this last week. What I was going to do uh, is I typically do this in my classes anyhow. So you guys have already taken, quote unquote, 2 exams. What I'm doing right now is I guess I gotta learn how to spell before anything. What a train wreck. So I'm finalizing your exam scores, and so what I'm doing is, and it's kind of a pain. I got to figure out a better way of doing it because obviously I don't have physical exams. So one of the things Canvas lets you do is you can download these exams, and then I grade them. And what I didn't realize at first is that there's like I guess I should have thought of this. I didn't realize they had it. They have like an annotation tool on Canvas, which I could have just graded them right from the reader. But what I've been doing is grading them and then trying to put comments back into your exam at the later date. So anyhow, it took longer than I anticipated. But anyhow, I should have that finalized today. And then basically you're going to get you'll see 2 scores on Canvas when I update the grade book. You'll see your exam 1 and your exam 2, but those are both going to be slightly modified for some of you based on how I decided to grade and combine scores. It'll be all self-explanatory. I don't think you need to worry about any of that. So what I mean is that sometime later today, perhaps tomorrow at the latest, at that point, your grades will be on Canvas. And I don't know that you guys, I don't even know if you're the same way. One of the trends that I've seen over the last maybe 2-3 years is that everybody is, I guess because schools now, when you're in high school and in elementary school or whatever, your grades are constantly updated on the internet. And so I guess students expect this, which is something I've never been used to doing. I mean, when I was a student, you got your grades at the end of the semester. But now everybody wants their grades updated. So I'm trying to adjust so that your grades are constantly updated. And I'm learning, especially with this virtual stuff as well. So I don't know. I hope you bear with me. I don't think any of you are going to be mad. And I don't know. But if there's something you're concerned about with your grade, or if whatever, please let me know. Typically, if I'm concerned about your grade, I'll reach out to you. And I'm not really there with any of you right now. So, of course, maybe you're like, I don't even know what that means. That said, if there's something about your grade you're concerned about, or if you think I maybe didn't get assignments from you or whatever, just reach out, let me know. Or you can wait a day or so, and then you should see your grades on Canvas once I type them in. Does anybody have any questions about that while we're talking about it? Anybody? Going once, going twice? Okay, good. I shouldn't say good, that's mean, but okay, and then the other thing to think about, which I don't know, it's kind of crazy to actually put it this way, but next week is the last week of class. So, I mean, we essentially have 4 more of these Zoom meetings, and what I'll do is I'll give you one more, it'll be similar to what you just did last week. And that's just how we're going to do it, because it's quarantine, or not quarantine anymore, although we might be going back to red, I heard. But this is the virtual learning world right now, and the best way I can figure out how to make life is sort of, I want to say easy, that's a bad word, but in my opinion, this is the best way to do this on short planning and all the stuff we've been under. So If you like it, great. If you hate what we're doing, then I apologize, but blame someone. I don't know, blame biology, blame the news, whatever. It depends on what political way you lean, I guess. Blame someone, just don't blame me. Or you can blame me, that's fine too. All right, anyhow, so we will have 4 more of these get-togethers, and we'll talk some physics, and then we'll ask you to do problems about them. And then hopefully you guys all do the problems real well next week, and then everybody gets an A. We hope. That's the goal. So what I would encourage you to do, I don't know what your week looks like next week as far as life and or life and or your schooling. I have no idea what you kind of pressures you're under with your other classes. Maybe you don't have any situations, but my initial plan was to give you guys an exam after class on Wednesday and then give you a couple days to do it. So if that's a logistic issue for some of you or all of you, let me know and we can adjust accordingly. Some of you might say, well, can we have it earlier? And I don't know that you can or can't, but the problem is there's definitely going to be stuff we talk about on Wednesday that, you know, it's kind of one of the things that stinks about sort of the way we're doing things now is in some ways we're testing you on some stuff that, you know, we haven't really had a chance to assess you on yet, but I guess sometimes that's the way it works. So anyhow, if you guys have an issue with doing an exam, say next Wednesday and Thursday, or that's not going to take you 2 days, I would hope not. But if late next week is bad for you, please reach out to me, whether you do it now, or if you think about it tonight and send me an email. Let me know what your sort of logistic issues are, and then we'll work from there. Does anybody have anything to say about that right now, or should I just assume you'll let me know otherwise? No? Okay. All right, you guys are very non-talkative, which could be good or bad. Okay, then let's do some physics. Let's pick a color here. We have purple. Let's go green. It's so cute. Okay, so what we've been talking about is let's say it real fancy, the movement of electric charge, which we have defined to be electricity. So we spent some time talking about these terms and some very basic sort of laws and ideas. We talked about electric fields, and then we talked about these point charges and protons and electrons. And then we talked about this idea of Ohm's law, which relates voltage, or if you want another fancy name for voltage is what we call potential difference. And so what we want to do is move on from that to sort of a little more detail of that. So let us do that. So a common way to study sort of electricity is to use these sort of diagrams. And what they're called electric circuits. Now, you've most likely seen these in the real world before. Maybe not as dumbed down as we're going to do them, or, you know, look at them from this sort of academic viewpoint or the learning viewpoint. Maybe you've had a remote control open before, or you've seen the inside of a phone or any electronic device, and what you'll see is typically what we call a board, a circuit board, and it'll have different wires and little different things all glued onto it. And that's the electric part that makes everything work. And so what we want to do is understand how that stuff works. And so we'll do that from a very basic viewpoint, and we'll do that by drawing what are called electric circuit diagrams. And we're going to do this from a very simplified viewpoint. So it turns out that there's two types of ways that this works. And if you can go Google the history of it, there's actually some pretty good stories about, maybe you watched the movie that came out, I think it was last year, about Tesla and his enemy when it comes to determining what's the best way to get electricity to people. So one of the things that happened in the late 1800s was people were figuring out how to use electricity effectively. And you had someone who you learned about in school named Thomas Edison, and he had a certain idea. And then the idea that he had was sort of opposite from another very famous and successful scientist whose name is now a car company. So this guy, Tesla. And anyhow, what they realized is that there was sort of two ways of getting electricity from one place or to the other. And one's called direct and the other's called alternating. And you've probably heard of this at some point, or maybe you like the band AC/DC. But nonetheless, we're going to talk about them. So there's two ways to do this. And this we're going to kind of use English words here. The first way is one direction, which we call direct current, which is denoted DC. And then the other way is it alternates direction. And by the way, let's put direction. I mean, really, what does this mean? We're using these words very loosely. So what we want to do is we want to visualize how charge moves. So remember, we're saying that the movement of charge is sort of our definition of electricity, right? But what is current? Well, if you go back to what we talked about last week, current is how we quantify the movement of charge. So current was defined as the change in charge over change in time. So it's sort of like a rate of change, like a speed or a velocity. But what we're doing is we're measuring or we're quantifying how charge moves over time. So a good way to visualize this is imagine you just have a wire. And so direct current means that the charge just moves, say, left to right. That's it, just moves left to right. But alternating current would mean that it could move left to right or right to left, depending on whatever it felt like doing. So what we know is we know that charge moves in one of those two ways. And so what we want to do is we want to recognize that and then quantify and use it at our disposal. So for example, things in your house like the outlets and how, things that you plug into the wall, that is typically alternating current. However, things that aren't alternating currents, like maybe you have a toy or a flashlight's a good example where you're putting a battery in. Typically, that type of current is direct, so DC. So it is important to understand that there's two ways of doing this, and then it's important to study them if you can. Now, it turns out alternating current's a little more difficult to study, so we're going to skip that, and we'll talk mostly about DC current because it's a little easier to do for us and for our purposes. So we're only going to study DC. Okay, here is a basic, a very basic thing we can do. So here's a very basic model. It consists of a battery, a switch, and a resistor. So a very sort of, I don't want to say it's naive, but a very simple way of thinking about this is a battery is your source of power. And it wants to give, for a lack of a better word, it wants to give electricity to whatever you want to give it to. And we typically have a switch that regulates if are we going to let the electricity pass? Are we going to let the energy or the power go? Or are we going to stop it? So you would imagine a flashlight, for example, has a switch. If you have it off, the battery's not doing anything. If you connect the switch, then, the quote unquote circuit is complete and the electricity, or let me be more physically sound, the current is allowed to move along the circuit. So imagine, if you will, you have just think of this as like, if you want, you can actually visualize this as wire. So let's imagine we have a battery. So let's draw what this might look like. And remember, when we think about charge, we think about having a positive and a negative charge. And many of you have seen a battery before, and you will notice that on a battery, there's a plus and a minus sign on different sides. And that is exactly what you would think it means if you paid attention to class on last Wednesday. So how do we recognize that there's a positive and a negative? Well, we might say, okay, here's our battery. We typically draw it that looks like this, and we label one side as positive and one side as negative. And then we have to sort of have a convention. And the convention is that we imagine the electricity moving from the positive. I keep saying electricity. That's kind of cheating. Imagine the charge moving from the positive part of the battery, and it wants to go to the negative side. So let's imagine that you have charge moving here, and then it stops for a second. Why does it stop? Well, we have some sort of switch. So if I take this switch, I can move it up or down. Let's use a different color so that we're very clear sort of how we want to do this. So right now that switch is open. And so when it's open, my current can't move because it just goes out here. It doesn't have anywhere to go to. But then I can imagine that my wire turns and then it comes over here. And let's throw a resistor in there. What does the resistor do? Well, the resistor resists the movement for whatever reason. Maybe it doesn't want to use more battery than it actually needs. So this is how we would draw our resistor. Hold on one second. I got a crying kid. Pardon me. Don't be mad. I'll be back in a second. All right, we're back. Okay, so so a couple things. Again, imagine, if you will, or the convention is a better way of saying it. So convention is imagine charge moving along this circuit from plus to minus in the clockwise direction. So again, and you know, I don't want to get into too many of the technicalities or the physics, but again, there's nothing wrong with you imagining sort of like these, you know, charge moving along this. Think of this circuit as maybe it's wire. I don't know how you want to think about it. So what we're saying is when that switch is closed, there is only one path for that charge to move. So the current can go one way if we're just assuming that it's direct. And so the convention is, what we want you to think about is that a current goes from plus to minus. So it starts on the plus side of the battery and it goes around and does what it needs to do, and then it comes back to the minus side. So someone once asked me this question, and they're like, why do we need a resistor? And then, you know, I thought to myself that, you know, that's a good question. I mean, all different devices that rely on electricity need different types of resistors or different strengths. And probably the best thing I could say is, why do we need resistors? Well, we can't just make I mean, I guess we could, but you don't want to make a unique battery for every single device that requires electricity or some sort of current. And so what as you guys know, there's sort of like your standard batteries. There's a double A, there's triple A, there's 9-volt, blah, blah, blah. And then you have these different types of batteries for things that, you know, or, you know, you see the little round ones, maybe a garage door opener or a watch battery. And so the thing is, we have sort of standard batteries. And so in order to adapt any device that needs some sort of voltage from a battery, we do things like add resistors, or as you can also imagine, capacitors. So perhaps one of the most basic examples of an electric circuit that we can draw would be something like this. Don't forget, this resistor resists the current that wants to move. And we know that we can quantify that, so that's one of the first things we do. All right, so we got tears upstairs. So suppose we wanted to add a second resistor. Well, there's two ways we can do that. So the first way, the official name for it is called series, and the second is called parallel. And you've actually probably seen this in action maybe not with resistors, but maybe you've seen different devices that require batteries. And sometimes when you put batteries, say for example, I have remote control for my television and stuff at my house, and some remote controls put the batteries next to each other, side by side. Other electronic devices might put the batteries on top of one another. So, I mean, maybe if each pen is a battery, you could say this is one way of putting two batteries together, or two resistors, if you will. And here's another way, perhaps like this. But if we look solely at the resistors for a second, and we look at how we might represent that in a diagram. So, you know, if you were going to draw this out, there's sort of two ways we might go about this. So let's break it down, series, and then we'll call this parallel. So in series, if we draw a similar thing that we drew before, we have our battery, have our switch. So if we have two resistors, one thing we might, well, that's bad. One way we might plot this creature in there is we might put a resistor like this. And then down the road, we might put another resistor. So it's typical to label these things. So we might, you know, we might call this guy V for our battery, our voltage, and we can call this guy maybe R sub 2 and R sub 1 here. And we imagine that it hits R sub 1 first, then it hits R sub 2. So that's what we say to be in series. But another way we might do this is we might say, okay, let's take two different paths. Perhaps we look like this. And so now we have two different resistors, but the path to get to them is different. So here we might call this guy R1 and this guy R2. Of course, here's our voltage, our battery. But you'll notice if it goes through R1, it doesn't go through R2, it being the current. And if it goes through R2, then it's not going through R1. So there's sort of the proverbial fork in the road here, if you will. So the question then becomes, do both circuits treat, let's remind ourselves what the current is. The current, remember, we use the letter I. So another way to think about this is when you hit that switch and the current starts moving, the current that gets back to the battery, is it the same in both cases? That's the thing to think about, yeah. All right, what do you want me to do? I know. All right, hold on one second. All right, sorry about that. So the question is, what happens to the current? How much is it resisted in series? How much is it resisted in parallel? And don't forget, we have a relationship through Ohm's law, and we can sort of do, through experiment and then also through theory, how does this happen? Or I shouldn't say how does this happen. What is the actual effect? So luckily, people have done these things, and we can quantify it. So so in series, we just add up. So let's say our resistance total is equal to the resistance of the first one plus the resistance of the second one. Now, unfortunately, it's not as simple in the case of parallel. Although there is a pattern. So here, 1 divided by the total resistance is equal to 1 over R1 plus 1 over R2. So we're using these reciprocals now. So what we say is one of the things we say, or one of the ways to phrase this in English is we say that they add inversely. So again, one of the things that students often ask, or not just students, maybe your own curiosity, say, well, why do we need certain things in series? Why do we want certain things in parallel? Well, it just depends. Taking out just resistors, but thinking about an electric circuit in general, imagine if your house, the electric circuit in your house was all in series. Well, then if one thing went bad, everything would go bad. So, not go bad, but it wouldn't get electricity or current. I keep saying electricity incorrectly. So, I mean, think about your house. I mean, if you've ever had a fuse blow or you've ever had to have electric work done at your, and maybe you haven't, I don't know. So, and compare that to if you've ever had, like, I don't know, if you celebrate Christmas or the holidays and you put lights outside of your house. And one of the things that's annoying about many, like, sets of Christmas lights is if one bulb goes out, the rest of them do, because it's not in parallel, it's in series. And so if one piece of that series is missing, then the whole shebang cannot be completed. The circuit can't be completed. So the one thing we should say is that this adds, this is not just limited to 2 resistors or 2, just 2 resistors. This extends to any number of resistors. So So for example, R total in series would be R1 plus R2 plus R sub 3, and who knows how many you have. Maybe you have N of them. And then of course, if you're doing it in parallel, so if you're interested in, you could go to Google and just go Google simple electric circuits, or just Google electric circuits and go to images, and you'll see things as simple as what we just drew, but you'll also see things that are much more complicated than what we drew. I think you guys would imagine that the electric circuit used for a flashlight would be much simpler than one used to sort of provide electricity to your house. And I think you would imagine that the electric circuit for a house is going to be a much less sophisticated than one for like a hospital. So hopefully your intuition is useful in these particular circumstances. So let's sort of do a typical problem. Before we do that, does anybody have a question? Okay, so let's do it. So get my colors here. So we're going to do 3 examples, and then we'll sort of move on. So here's a typical example. Determine total current of the circuit below. So let's draw. We'll ignore the switch. So let's imagine we have our battery, and we need to give it a numerical value. So let's say it's V equals 5 volts. And then let's put 2 terribly drawn resistors in series. So let's suppose that R sub 1 is, I don't know, how about 20 ohms? Remember, resistors are measured in ohms. And then R sub 2, let's say, I don't know, 100 ohms. Okay, so what is the total current? Well, the total current given by Ohm's law says that V equals IR, voltage equals I times R. So we don't want that, we want total current. So we need current, which is going to be voltage divided by R. So notice how notice what I'm doing here. I wrote R in blue. It has no subscripts, and I have the resistors R sub 1 and R sub 2. They do have subscripts. So by context, R, the blue R with no subscripts, that's going to represent our total resistance. And so we know that since these guys are in series, so these guys are in series, and that implies that R equals R sub 1 plus R sub 2. So what we can easily calculate then is the total current is voltage, which is 5 volts, divided by 120 ohms. And then all that's left to do is do the division, 5 divided by 120. And so 20 goes, or excuse me, losing my mind. 5 goes into 120 24 times. So what you could do is you could say this is 1/24. Now, what are the units here? What are the units for current? Remember, a current is an amp. So if you write it in an exact value, it's 1/24 amps. Or if you write it in the decimal approximation, it's 0.042 if you round it up. Does anybody have a question, comment, concern? All right, so let's do another example. This is an example where they are in series. Let's do another one. So now we'll draw a scenario where they're in parallel. Maybe we'll draw our battery different this time. Plus, let's go up like this. I'm not good at drawing these resistors. I need to go back to 7th grade art class. So we'll call this R1. We'll call this R2. Let's say our volts, how about 10 volts? And let's assume that R sub 1 is, let's say, 10 ohms, and this is 50 ohms. That's ugly. Let's clean that up. Write it over here so it's not so ugly. So what is the current? Well, we know current is voltage over R. Now, these guys are in parallel, which means we have a little work to do before it's not as straightforward as the previous problem. So what is R? Well, we know 1 over R has to be equal to 1 over R sub 1 plus 1 over R sub 2. So this is some uglier mathematics. And so this is 1 over 10 plus 1 over 50 . Now, one of the common errors that we'll see is that sort of sometimes we get too quick when we're doing this and we do it wrong. So if you add 1/10 and 1/50th, you get 50 plus 10, which is 60 over 500. So what this reduces to is this reduces to 3/25. So what you end up getting is you get 1 over R is equal to 3 over 25. And what that tells you is that R is 25 over 3. So if we plug these numbers in, that's 10 volts over R, which is 25 over 3 ohms. Which is 30 over 25 amps. And if you want to write that instead of using fractions, that's what? 25 goes into 30 one time, remainder 5, so 1.2. All right, does anybody have a question about this? The calculation, I hope it's clear. You know, these are sort of our, you know, what's done in the blue is sort of the first step calculation to get the total resistance. Does anybody have a question? Comment? Everybody's sleeping, taking a nap. All right. Let's do one more. Number 3. All right, so the last one we'll do is let's not say next. This is our last one. Let's just. So what if we have both series and parallel. So let's draw this, and then let's think about the natural, or what way we think we would go about it. So let's, for fun, we'll put our battery over here. Our battery comes down, it's going to hit a resistor. And then we're going to have a resistor and another resistor. These guys are in parallel. So let's call this R sub 1, and then we'll call this guy R sub 2, and let's call this guy R sub 3. And let's give all these guys values. So for example, let's say our voltage once again is 10 volts. And then over here, let's give these guys R sub 1, let's say it's 5 ohms. R sub 2 is 20 ohms. And then R sub 3. Let's say 50 ohms. Okay, so we have to decide how should this be done, and in what order seems reasonable and even logical. So the first thing you have to realize, and this is a common error, is that let's write this down, because we have to think, again, by our convention, we're moving from positive to negative. So if you put your finger on this battery and say, okay, I'm going to trace it around from positive to negative, what do I hit first? Well, I hit R sub 1 first. I hit that resistor. And then once I hit that, then I have the fork in the road, or the split. So I have two resistors in parallel. So the thing to note is R1 is not in series with R2, and it's not in series with R3. R1 is in series with something that's equivalent to the combination of R2 and R3. So it's important to understand that. So first, we need an equivalent resistance to the parallel R2 and R3. Well, we know what that is. That's 1 over R. We'll call it R sub 4, because we didn't, we're using subscripts. And then that is 1 over R sub 2 plus 1 over R sub 3. Now, that is 1 over 20 plus 1 over 50, right? So if we do that arithmetic, you get a common denominator, and maybe you guys probably aren't as, I mean, you can use a calculator if you want, but what this equals is this equals so 50 times 20, 50 plus 20 is 70. So you get 70 over what? 1,000. So you end up simplifying it to 7/100ths. So if I get my eraser, this becomes 7 over 100. So in other words, we have the following thing. So what I want to do is I want to replace this circuit with one that's a little, I have an equivalent circuit now, at least if I believe the rules that we said about parallel resistors. So if we believe these things, then what we can draw is the following. So so our original circuit is equivalent to, now let's draw the new guy. So once again, we have our battery here, plus minus, what was our battery? 10 volts, I think. Was it 10? Let's double check. Yep, 10. And then we had R1, which was 5. So it comes down here, hits this R1, which was 5 ohms. And then it had these two guys in parallel. But we were going to replace them with a equivalent resistor. What's the equivalent resistor? Well, it looks like this. So what did we find it to be? Well, we found that 1 over that resistance is 7 over 100. So that means if we invert it, this guy, which we called R sub 4, is 100 over 7 ohms. And so then now we can simply just add, these guys are now in series. So what we end up having is that I, which is V over R, becomes V, which is 10 volts over. Now, so since these guys are in series, we know now that R is R1 plus R4. So then you have to take 100 over 7 plus 5. R sub 1 is 5, and then R sub 4 is 100 over 7. And so if you do this, then you end up getting 135 over 7 ohms. Okay, so then you're just left to do the arithmetic. So 10 divided by 135 over 7 is 70 divided by 135. So this equals what? 70 over 135, which will reduce to 14 over 27 volts over ohms. So this is 0.52 amps. Whew. Okay, so these are 3 typical examples of circuits, and these are things that you should definitely look again. I go back to this, and we've had these sort of conversations about like real world versus school versus look, this is a physics class, and one of the things we're supposed to teach you is physics, particularly a survey of fundamental physics, and this is part of it. Now you might say, oh, what is this good for? When am I ever going to need that? You know, I don't know. That's debatable, I guess. But one of the things we teach in physics is electric circuits. And so that's why we're asking you to do this. And so there you are. So hopefully you'll study these examples and you'll do some problems that we give you, and then all's great. Does anybody have a question about this? All right, so two more things before we sort of go to a more general sort of conversation about all this. Okay, so two more sort of quantifying things. So here's a good way to think about it. If we imagine charge is moving through our circuit, and anytime we have things moving, we realize that there's work done. And so we have things like kinetic energy, we have things like potential energy. We ask sort of how do we quantify these from that viewpoint. So here's what we have to think about. So when a charge moves across V, the voltage, so a change in electric potential energy occurs. So if you remember last week, we talked about this electric potential energy, and we talked about electric potential. And you remember that we used the letter U for electric potential energy, and then we used the letter V for the electric potential. So how is this given? So well, the relationship is that the change in electric potential is the change in charge times voltage. So again, we defined what U was last week. U is this electric potential energy. V is the potential difference, or the voltage. And so they are related this way. So here's a cool thing that we can do. So let's divide both sides by the change in time. So I'm going to divide both sides by the change in time. So if I do that on the next page, you're left with the change in U over the change in time is the change in charge times voltage over the change in time. But what we can do is we can recognize, we know what the left-hand side is and we know what the right-hand side is. So if we sort of rewrite this, this is change in U over change in time plus change, no, not plus, this is equals. So if we're thinking ahead, if we're thinking like, okay, and I've used this sort of story before, if we're thinking about a better way of describing the situation, if I write it like this, then what is change in Q over change in time? Well, that's just current. So perhaps I'll write this slightly differently. We'll just end this here, and let's sort of get in our time machines and go back to what is change in energy over change in time? Well, if you go way back to many classes ago, that is power. So the expression this is the definition of power. Similarly, the expression change in charge over time is the definition of current. And so that means that the above formula can actually be written in a much, I don't want to say much more useful way, but in a form that can be used in many ways. And that is, we get the relationship that power is equal to current times voltage. So you need to understand, and this is something that is often confusing. Sometimes we see the I and the V and then we think Ohm's law, but this is not Ohm's law. Ohm's law says that current, resistance, and voltage have a relationship. That is built into this, but this is also still an expression for power. And another interesting thing to think about with this definition is its connection with, I won't say definition, I guess that's a poor way of saying it. We're not defining that power. Power is defined to be the change in energy over time, or the rate at which energy is consumed, is an English way of saying that, or is a way of saying it in English. But if you study these equations, what you get is you get an expression for energy in terms of power and time. So, when you're talking about looking at your monthly bills and you look at, I don't know who your electric provider is, but I pay my electric bill. For a while, I paid it to this company called Direct Energy, and they called it the energy bill. And the reason for that is because energy is power multiplied by time. And you could see that from these equations. Does anybody have a question? Comments, concerns? I say that all the time. No one ever has a comment or a concern. Okay, so based on these equations, you know, one of the things that we can do is we can say, all right, how much would the energy bill be for, you know, a house or for a hospital or something like that, based on an average amount of power used. Okay. So the next thing we need to talk about then is something that should be near and dear to your hearts. And that is electric safety. So, you know, I feel like there's a couple ways we can talk about this, and probably the best way is not from, you know, you guys are all educated, you're adults, you're well-rounded, at least that I can tell. You know, for me to define things that you can easily look up, particularly definitions, seems almost sort of insulting to your intelligence. It's one thing for us to do problems that involve equations and things that you're less familiar with, and derive things and do computations. But for me to say, here's this and here's that, but when it's something that you can easily Google and look up, that's very insulting, not just to your intelligence, but also in my opinion, it's disrespectful of your time. So what I do want to do, and obviously there'll be a platform if you want to discuss any of these things, because it's going to be on your next homework assignment. So these are things that you'll be asked to define, discuss, etc. On homework. So number one, most importantly, is what we call electric shock, or electrocuted, as people like to say. And things such as macro shock, micro shock, so, you know, just again, these might be words you're familiar with. I don't know. These are things that, you know, I would imagine you should be familiar with if you're in certain settings in healthcare, maybe in, you know, an emergency room, or you're doing certain things. Like, I was fascinated. A friend of mine, it's not really a friend, it's a friend of a friend, so it's more of an acquaintance, but he's like 42 and he had a heart attack about a month ago, and now he has a pacemaker. And so we were discussing this, and one of the kids goes, how does it work? And so we were like, well, basically it just like shocks the heart, you know, to keep it going. And then of course the kid goes, well, you tell me that shocking will kill me. You know, because of course you tell kids not to touch plugs and play with electricity because they'll get electrocuted, right? And so it's a great sort of way to sort of analyze this idea of what is macro shock, what is micro shock. Why do certain things kill you? Why do other things not kill you? At least when it comes to electricity. So these are terms, if you're not familiar with, and even if you are, that I would highly encourage that you sort of spend some time defining them. Think about how to quantify them, even, you know, it's one thing to define them, but can you quantify them? Can you give examples of one? So, and when I say quantifying, what I mean is there, look, macro shock and micro shock, I don't know how familiar you are with these macros and micros. Maybe you took economics and you understand why we call something macro versus micro. I don't know. There's lots of places these show up in life where we use these words macro and micro. But when I say quantify them, what does that mean in terms of, like, say, amps? What's the difference in amps between micro shock and macro shock? Another thing to ponder, why is it in our house we have circuit breakers? Why do we have fuses? Have you ever thought about any of that stuff? Is it a safety reason? Is it a simplification reason? Is it a combination of both? If you've ever purchased a house in the last few years, or actually more, if you've ever had to sell a house, which maybe, I don't know if you have, there's all kinds of safety requirements on what kind of, outlets or receptacles you can have on your house, inside, outside. If they're near water, they have to be a certain thing. When I say a certain thing, they have to be of a certain class of safety. Maybe you've heard of what a GFI is before. What does GFI mean? What does it mean to be grounded? So these are questions. And maybe some of you have played with electricity before. I don't know. Do you know what a hot wire is? Do you know what a cold wire is? Or not cold, ground, neutral. So these are things that, again, we would hope that, as humans, we have a certain understanding. I shouldn't say as humans, as adults, we have a certain understanding and respect for electricity, even if we don't quite know how it works. But it would be useful, going forward for you, if not, you can do these sort of circuit problems, but that you can understand sort of the more general picture. We're doing those simple circuit problems, and we're talking about this many amps and this many amps, or find the total current. Well, how does that apply to things like being electrocuted, for a lack of a better word? Another interesting thing you might want to read about is, maybe you at your house, or, sometimes we lose power when it storms, or maybe that's, if you lose power when it storms, that's typically because the electricity coming to your house has been cut off somehow. But other times things go bad, like a fuse goes. What causes that? How does a fuse work? Maybe you've had GFIs in your house shut off, and then you're like, oh, my plug doesn't work. And then you have to go around and press the little button in. What is that doing? How does it work? So these will be questions that we might, ask of you. And these are things, look, I'm not going to insult your intelligence, as I said before, and waste your time. I mean, these are things that we can look up. These are things that we can learn on our own. So anyhow, these are things I'm going to ask you to at least ponder. Does anybody have a question or a comment? I know, and the other thing that you can also think about electricity too. And again, I know that we don't think about all the science behind things we use. I mean, I know I'm sitting in a computer right now, and while I know a little bit about how all this stuff works, I'm not really thinking about how all these monitors and this tablet and all this is. I'm not thinking about all the specifics of that stuff. Just like I've used numerous times, you're probably not when you're dealing with instruments in your workplace. But it is something that it is a fundamental thing. And you guys, I guess you would probably even look. I mean, it's not like we're doing this stuff in 1910. I mean, now you guys, look in a doctor's office or an operating room, or the emergency room, for example. I mean, you see technology all around you, electricity everywhere, machines plugged in, all kinds of gadgets beeping and buzzing, and we often use electricity to do surgeries now. So these are things that I would ask you to read about and think about, and we'll do that. We'll give you questions and things to write about on the homework. Does anybody have a question? Okay. If you guys don't have questions, I say thank you, and we'll pick up on Wednesday. I'm going to post an assignment in a little bit, and then you guys can work on that. And then I'll get your grades updated and everything. So if there's anything you want to discuss, we can do that. All right. Well, thank you, guys.
Thank you.
Take care. Oh, they're awake. They're awake. I need 4 left. Have a good one, everybody. Take care. All right. How do I get out of here? And bye-bye.